Imagine a planet not orbiting a star, not bathed in sunlight, not held in the gravitational embrace of any solar system. A world alone, hurtling through the absolute darkness of interstellar space at hundreds of thousands of kilometers per hour. No sunrise, no sunset, just eternal night. Surface temperatures approaching absolute zero. Ice covering ancient oceans. Atmospheres frozen solid and fallen as snow. For decades, we believed planets required stars. That the very definition of a planet meant something tethered to a sun, dancing in its light. We were wrong. There are more orphaned worlds drifting through the void between stars than there are stars themselves. Billions upon billions of rogue planets, ejected, abandoned, wandering. Some may harbor life beneath frozen crusts. Some may have been home to civilizations that watched their sun disappear into the distance. Some approach our solar system right now, invisible against the cosmic dark. What if I told you that the space between stars isn't empty at all, but crowded with more planets than all the solar systems in the galaxy combined? Today, we journey through evidence that challenges everything we thought we knew about planets, solar systems, and the true architecture of our galaxy.
And just before we begin, if these quiet moments of curiosity have become a gentle part of your evening, liking or subscribing is a wonderful way to support the channel. It lets these explorations continue and helps welcome others looking for a moment of calm in the vastness of what we're about to explore. The story begins with an impossibility. November 2011. A global network of telescopes focused on a seemingly empty patch of sky in the constellation Sagittarius, toward the galactic center. The telescopes weren't looking at stars, they were looking at the darkness between them, searching for something that shouldn't exist. Dr. Takahiro Sumi and his team at the Microlensing Observations in Astrophysics Collaboration had spent years developing a technique to see the invisible. Gravitational microlensing, using Einstein's prediction that massive objects bend space-time itself, acting as natural magnifying glasses for light from distant stars. The data appeared as a brief brightening, a background star, magnified for just a few hours before returning to normal brightness. But the signature was wrong. The mathematical curve didn't match a star passing in front of another star. It matched something smaller, much smaller, a planet. But there was no star, no binary companion, no host system whatsoever. The mass calculations revealed an object approximately the size of Jupiter drifting alone through interstellar space, 60 light-years from Earth. They named the phenomenon MOA-2011-BLG-262. A rogue planet, an orphaned world, a wanderer. The discovery shouldn't have been possible according to planetary formation theory as it stood in 2011. Planets form from the protoplanetary disks surrounding young stars. They condense from gas and dust, growing within the gravitational and thermal environment of their parent star. A planet without a star was like finding a child without parents, without ancestry, without origin. But the evidence was undeniable. The gravitational signature matched theoretical predictions for an unbound planetary mass object. The timescale of the brightening event, just a few hours, indicated something too small to be a star, yet massive enough to significantly bend light. Within months, the MOA team identified several more candidates. Each detection represented a brief moment when one of these invisible wanderers passed directly in front of a background star from our perspective, betraying its presence through the temporary magnification of that star's light. The implications rippled through the astronomical community. If these objects could be detected at all, given how extraordinarily rare such perfect alignments must be, then there must be an enormous number of them. The detection rate suggested something staggering. For every star in the Milky Way, there might be multiple rogue planets drifting through the darkness. Think about that number. 400 billion stars in our galaxy, perhaps 1 trillion or more rogue planets, an invisible population larger than all the bound solar systems combined. The concept of rogue planets wasn't entirely new. In 1996, astronomers had detected brown dwarfs, objects too small to sustain hydrogen fusion like stars, yet too large to be considered planets, floating freely in stellar nurseries. Some theorists speculated that smaller objects might also be ejected during the chaotic early days of solar system formation. Computer simulations in the early 2000s by Dr. David Bennett and others had predicted that planetary ejection should be common. When multiple planets form in a young solar system, their gravitational interactions create a cosmic game of billiards. Planets migrate, orbits destabilize, and in the resulting chaos, some planets get flung into interstellar space entirely. The simulations suggested that for every stable solar system we observe, multiple planets likely got ejected during its formation. Jupiter-mass planets, Neptune-mass planets, even Earth-mass worlds thrown into the void. But simulation is one thing, observation is another. The 2011 detection by the MOA team provided the first concrete evidence that these simulations reflected reality. The galaxy harbored a vast, invisible population, a dark ocean of orphaned worlds between the lights we call stars. Understanding how we detect these invisible objects is crucial to understanding what they tell us about the universe. Gravitational microlensing works because of Einstein's general relativity. Mass warps space-time. When a massive object passes between us and a distant star, the space-time curvature bends and focuses the star's light, temporarily brightening it from our perspective. The degree of brightening and the duration of the event reveals the mass of the lensing object. A star creates a distinctive curve lasting weeks or months. A planet creates a much briefer event, hours to days, with a characteristic shape to the light curve. But here's the remarkable part. Detecting a rogue planet requires almost perfect alignment. The planet, the distant background star, and Earth must line up within a tiny angular tolerance. The probability of such alignment is microscopic. Yet the MOA survey detected multiple events. The OGLE survey, optical gravitational lensing experiment, detected more. The mathematics became inescapable. To see even a handful of these rare alignment events meant there must be an enormous population of rogue planets. Dr. Takahiro Sumi's team published their statistical analysis in Nature in 2011. Their conclusion: Jupiter-mass rogue planets likely outnumber stars in the galaxy by a factor of nearly 2 to 1. 2 rogue Jupiters for every star. The number seemed absurd, yet the evidence supported it. Following the 2011 announcement, the flood began. More detections, more statistical analyses, more confirmation of the impossible. In 2017, astronomers using the Pawn-STARRS survey in Hawaii identified PSO-J 318.5-22, an object drifting alone through space just 80 light-years away. Mass, approximately 6 times Jupiter. Age, about 12 million years based on its infrared signature. No star in sight. The Spitzer telescope identified several more candidates. Young, warm rogue planets, still glowing with the heat of their formation, visible in infrared wavelengths even without a nearby star to illuminate them. By 2020, the known catalog of rogue planet candidates had grown to dozens, with statistical models suggesting the galaxy contained not billions, but trillions of these objects. Each detection refined the models. Each statistical analysis narrowed the uncertainties of the surprise numbers. The conclusion remained consistent. Rogue planets vastly outnumber stars. But the evidence forces us to confront an uncomfortable possibility. If the galaxy contains trillions of invisible worlds, what else are we missing? What portion of the universe's mass drifts unseen between the lights we've always assumed constituted the cosmos? And more troubling still, where did they all come from?
To understand the population of rogue planets, we must understand how solar systems form and how they destroy themselves. In 2005, Dr. Hal Levinson at the Southwest Research Institute ran detailed simulations of early solar system dynamics. His team modeled what happens when multiple gas giants form in close proximity within a young protoplanetary disk. The results were violent. Gravitational interactions between massive planets create orbital resonances, regions where the orbital periods create reinforcing gravitational tugs. These resonances amplify over time. Orbits that appear stable for millions of years suddenly destabilize. Planets migrate inward or outward. Some collide. Others achieve escape velocity, flung into interstellar space by gravitational slingshot effects. The simulation suggested that in systems where 3 or more gas giants form, at least one typically gets ejected. In our own solar system, some models propose that we once had a 5th giant planet, ejected billions of years ago by interactions with Jupiter and Saturn. The NICE model, named for the French city where it was developed, describes the orbital chaos in our solar system's early history. Around 600 million years after formation, Jupiter and Saturn crossed a 2-to-1 orbital resonance. The resulting gravitational chaos scattered Uranus and Neptune outward and bombarded the inner solar system with comets in the late heavy bombardment. If our solar system experienced such violence, every solar system must experience it. Ejection isn't rare, it's inevitable. The mass distribution. Early detections focused on Jupiter mass rogues because they create the strongest microlensing signatures. But as detection techniques improved, astronomers began finding smaller objects. In 2016, a microlensing event designated OGLE 2012 BLG 1323 revealed an object with approximately half Jupiter's mass, drifting alone. No companion star within 10 astronomical units, 10 times Earth's distance from the Sun. Statistical analysis of microlensing events by Dr. Persmek Moroz and colleagues in 2017 suggested that smaller rogues might be even more common than Jupiter mass ones. For every rogue Jupiter, there might be 4 Neptune mass rogues. For every Neptune, perhaps 10 Earth mass rogues. The mathematics suggested something extraordinary. There could be 40 Earth mass rogue planets for every star in the galaxy. 40 drifting Earths for every sun. If accurate, that's 16 trillion Earth mass worlds wandering the Milky Way alone, invisible, frozen, silent. Some of those worlds likely harbored oceans before their ejection. Some may have had atmospheres, continents, possibly even primitive life. All of it flash frozen when the parent star receded into the distance, becoming just another point of light among billions. The formation alternatives. But not all rogue planets must be ejected from solar systems. Some may form directly in interstellar space, never bound to a star at all. In 2018, astronomers using the Atacama Large Millimeter Array in Chile discovered evidence for planetary mass objects forming in the cores of collapsing gas clouds, similar to how stars form, but on much smaller scales. Dr. Nuria Huelamo and her team observed a young stellar association called the Sigma Orionis cluster. Among the confirmed stars, they identified multiple objects below the mass threshold for stellar ignition, brown dwarfs and planetary mass objects, some as small as 3 Jupiter masses, apparently forming independently rather than being ejected from stellar systems. These objects weren't planets in the traditional sense. They didn't form from a protoplanetary disk. They condensed directly from interstellar gas like miniature failed stars. Some astronomers prefer the term sub-brown dwarfs or planetary mass objects rather than planets. But the functional result is the same: objects of planetary mass wandering through space without stars. If both ejection and direct formation contribute to the rogue planet population, the total numbers might even exceed the trillion-scale estimates. The galaxy might be even more crowded with dark, wandering worlds than anyone predicted. The speed and trajectories. Rogue planets don't simply float through space. They hurtle through it at tremendous velocities, typically ranging from 30 to 100 kilometers per second, over 100,000 kilometers per hour. These velocities reflect their origins. An ejected planet carries the orbital velocity it possessed when thrown from its parent system, plus the additional speed imparted by the gravitational slingshot effect. A planet forming independently inherits the velocity of the gas cloud that spawned it. Some rogues move even faster. In 2019, Astronomers identified a hypervelocity rogue planet candidate moving at over 200 kilometers per second, fast enough to potentially escape the galaxy entirely. Such extreme velocities suggest ejection from a close encounter with a supermassive black hole or a binary star system. The trajectories are essentially random. Rogues don't follow the orderly orbital paths of bound planets. They trace straight lines through three-dimensional space, affected only by the gravitational pull of the galaxy as a whole. This creates a fascinating dynamic. At any given moment, thousands of rogue planets pass through the volume of space occupied by our solar system. Most are far from the Sun, in the vast spaces between planetary orbits, but some pass closer. Statistical models suggest that a Jupiter-mass rogue passes within 1 light-year of the Sun approximately every million years. An Earth-mass rogue might pass within that distance every 100,000 years. We've never optically confirmed one during a close approach because they're essentially invisible unless they happen to pass precisely in front of a background star from our perspective. They might as well be ghosts. The demographics. By the early 2020s, multiple independent research teams had converged on similar population estimates using different methodologies. The MOA collaboration's ongoing surveys through 2021 confirmed their earlier estimates, approximately 0.25 to 2 Jupiter-mass rogues per main sequence star. The broad range reflects remaining uncertainties in detection efficiency and events duration statistics. The OGELE survey's data suggested similar numbers with perhaps higher populations of smaller mass objects. Dr. Takahiro Sumi's synthesis paper in 2023 combined data from multiple surveys spanning nearly 2 decades. The conclusion: the galaxy contains, at minimum, 100 billion free-floating Jupiter-mass planets, and likely several times that number when including smaller masses. At maximum estimates, incorporating the possibility of abundant Earth-mass rogues, the population could reach 2 trillion wandering worlds. 2 trillion planets without suns. To put this in perspective, if you could visit every rogue planet in the galaxy, spending just 1 second on each, it would take over 60,000 years to visit them all. The average distance between rogue planets in interstellar space is approximately 1 to 2 light-years, vastly closer together than stars, which average 4 light-years apart. The galaxy isn't mostly empty space dotted with solar systems. It's a sea of dark, wandering worlds with occasional islands of light. But this represents just one piece of a much larger puzzle hidden in the darkness between stars. Some rogue planets aren't entirely dark. Young rogues, those ejected relatively recently in cosmic terms, still glow with residual heat from their formation and from the energy of compression. The Spitzer Space Telescope, and later the James Webb Space Telescope, have detected several of these warm wanderers through their infrared emissions. Objects like CFB-DS IR 21490403, discovered in 2012, glow at temperatures around 400 degrees Celsius, hot enough to emit detectable infrared radiation even without a nearby star. But here's where it gets strange. In 2021, JWST infrared surveys of star-forming regions detected dozens of warm infrared sources that appeared to be isolated planetary mass objects. Many showed spectroscopic signatures of water vapor and methane in their atmospheres, atmospheric chemistry consistent with gas giant planets. The strange part, their infrared luminosity
didn't match standard cooling models. They were too bright. Something was keeping them warmer than gravitational contraction alone could explain. Dr. Kevin Luhman at Penn State proposed one explanation: tidal heating. If these rogues had large moons, perhaps captured during their ejection, the gravitational interaction between planet and moon could generate sustained tidal heating, similar to how Jupiter heats its moon Io through tidal flexing. A rogue planet with a large moon might maintain substantial internal heat for billions of years after ejection. The surface would still be frozen, but beneath ice crusts hundreds of kilometers thick, liquid water oceans might persist indefinitely. The implications are staggering. A rogue warm with subsurface oceans would be chemically and thermally suitable for life, despite floating through interstellar space light years from any star. This raises a crucial question. Can rogue planets retain moons during ejection? Simulations by Dr. Hagai Peretz in 2012 suggested that during violent ejection events, planets typically lose their satellite systems. The same gravitational chaos that flings a planet into interstellar space tends to strip away its moons. But some moons survive. Particularly large moons in close orbits, analogous to Earth's moon, can remain gravitationally bound during ejection. The probability depends on the ejection velocity and the specifics of the gravitational encounter. Statistical models suggest that perhaps 10% of ejected gas giants retain at least one moon. For Earth-mass rogues with large moons, the retention rate might be higher, possibly 30%. If these numbers hold across the trillion-planet population, there might be 100 billion rogue planets wandering the galaxy with intact moon systems. Some might have multiple moons, entire miniature solar systems drifting through the void, illuminated only by the faint infrared glow of their host planet. These moon systems create extraordinary possibilities. A large moon orbiting a rogue gas giant would experience tidal heating from its planet, just as Io experiences from Jupiter. This heating could maintain liquid water beneath ice crust, creating habitable environments completely independent of any star. Life wouldn't require sunlight. It would require only tidal heating, liquid water, and the right chemistry, precisely the conditions that might exist in these wandering systems.
Another critical question: do rogue planets retain atmospheres? When a planet is ejected, its surface temperature plummets. For a planet like Earth, ejection means that within years, average surface temperatures drop below -200 degrees Celsius. Oceans freeze, atmospheres begin to condense. But condense doesn't mean disappear. Dr. Dorian Abbott at the University of Chicago published simulations in 2011 showing that a planet with Earth's atmosphere and oceans, if suddenly ejected, would develop a thick ice crust over its oceans within a few million years. But beneath that ice, liquid water could persist almost indefinitely, kept warm by residual geological heat and radioactive decay in the planet's core. The atmosphere wouldn't vanish. It would freeze and fall as snow, eventually forming an insulating blanket of frozen nitrogen, oxygen, and carbon dioxide hundreds of meters thick. This frozen atmosphere would actually help preserve any subsurface oceans by providing additional insulation. For larger planets, super-Earths or mini-Neptunes, hydrogen-rich atmospheres might not freeze at all.
Hydrogen remains gaseous even at temperatures approaching absolute zero. A rogue super-Earth with a thick hydrogen atmosphere could maintain that atmosphere indefinitely, potentially keeping surface temperatures high enough through greenhouse effects to maintain liquid water. The most remarkable discovery involves atmospheres on rogue gas giants. Some of the warm infrared rogues detected by JWST show complex atmospheric chemistry, organic molecules, including ethane, acetylene, and hydrogen cyanide. These molecules form through photochemistry driven by internal heat rather than starlight. In other words, active atmospheric chemistry powered entirely by the planet's own warmth, occurring in total darkness light years from any star. This atmospheric chemistry raises an extraordinary possibility. On Earth, the first life likely emerged in deep-sea hydrothermal vents, environments completely independent of sunlight. The energy came from geochemical reactions and thermal vents, not photosynthesis. A rogue planet with subsurface oceans and ongoing geological activity could host similar hydrothermal environments. The chemistry would differ from Earth: no atmospheric oxygen, different dissolved gases, but the basic requirements for life would exist: liquid water, chemical energy, geological activity to cycle nutrients. Some researchers have gone further. Dr. Dimitra Atri proposed in 2019 that advanced life, even technological civilizations, might persist on rogue planets after ejection. A civilization with sufficient technology could survive the transition, building underground habitats and harnessing their planet's geothermal energy. From our perspective, such civilizations would be utterly invisible. No radio signals escape into space when there's no need for interplanetary communication, no optical signatures in a world of permanent night, just a frozen world drifting through the darkness, with perhaps billions of inhabitants living in complete isolation beneath kilometers of ice. The evidence extends beyond mere survival into the realm of adaptation. If life can persist on rogue planets, evolution continues. Complex ecosystems might develop in subsurface oceans powered entirely by geochemical chemistry, adapting across billions of years to environments we can barely imagine.
To understand what rogue planets tell us about the galaxy, we must reconstruct its true architecture. The visible Milky Way, the luminous spiral arms of stars we photograph, represents perhaps 10% of the galaxy's mass. Dark matter accounts for roughly 85%. The remaining 5% consists of gas, dust, and now, we realize, trillions of rogue planets. These wandering worlds constitute a significant fraction of the galaxy's baryonic matter, the ordinary matter made of atoms as opposed to dark matter. Some estimates suggest rogue planets might account for 1 to 2% of all baryonic mass in the galaxy. That's comparable to the mass contained in all stellar systems combined, including planets, asteroids, and comets. The galaxy isn't structured as we imagined, discrete solar systems floating in an empty void. It's better described as a continuum. Stellar systems represent local gravitational maxima, concentrations of matter bound by stars, but between these maxima, countless worlds continue their lonely orbits around the galactic center. Dr. Louis Strigari at Stanford University has proposed viewing the galaxy as a single gravitational structure with multiple components: a supermassive black hole at the center, a stellar disk, a dark matter halo, and a vast population of free-floating planets. Each component follows its own dynamics while contributing to the galaxy's overall gravitational architecture. This perspective transforms our understanding. We don't live in a solar system within an otherwise empty galaxy. We live in a galaxy almost completely filled with matter at varying densities, with our sun representing just one local peak in a vast, continuous mass distribution. The rogue planet population tells a story about galactic evolution. If most rogues were ejected during early solar system formation, their population should peak around 8 to 10 billion years ago, the era of maximum star formation in the Milky Way. Younger rogues, ejected more recently, would contribute a secondary population. But if many rogues formed directly in interstellar space, their formation should track star formation more closely, with ongoing rogue formation even today. Dr. Sean Raymond at the University of Bordeaux has combined planet formation simulations with galactic evolution models to trace the rogue planet population through cosmic time. His models suggest a complex history. In the galaxy's first billion years, few rogues existed. Star formation was just beginning, and solar systems were newly formed and still stabilizing. Between 5 and 10 billion years ago, rogue production peaked. This era saw maximum star formation and maximum planetary ejection. Billions of planets per year were thrown into interstellar space across the galaxy. Over the last 5 billion years, the production rate has declined but continued steadily. The galaxy still ejects millions of planets annually, roughly one every few seconds. The current rogue population represents the accumulated result of 12 billion years of stellar and planetary evolution. Every rogue tells a story of formation, survival, and eventual ejection. A planet that lost its sun.
Our solar system hasn't remained isolated from this wandering population. Statistical models suggest that over the Sun's 4.6 billion-year lifetime, approximately 5,000 rogue planets have passed within 1 light-year, close enough to potentially perturb the Oort cloud and send comets cascading into the inner solar system. Some may have passed much closer. Dr. Corian Baylor-Jones at the Max Planck Institute for Astronomy has calculated encounter probabilities using Gaia spacecraft data on stellar motions. His analysis suggests that roughly 100 planetary mass objects, either rogue planets or brown dwarfs, have passed within 0.5 light-years of the Sun during its history. A handful may have penetrated the inner Oort cloud, passing within 0.1 light-years, just 6,000 astronomical units. At such distances, a massive rogue could gravitationally perturb cometary orbits, potentially triggering comet showers that lasted millennia. Some researchers have speculated that past mass extinction events on Earth, particularly those not associated with obvious terrestrial causes, might correlate with close rogue encounters. The idea remains highly speculative, but it's worth noting that a massive rogue passing through the Oort cloud 66 million years ago could have set in motion the sequence of events that sent the Chicxulub impactor toward Earth. We have no direct evidence for such encounters, but the statistical probability is non-zero. And every day, more rogues drift through the galaxy, including some on trajectories that will eventually bring them into our cosmic neighborhood. The difficulty of detecting rogues explains why they remained hidden for so long. Optical telescopes are useless. Without reflected or emitted light, rogues are effectively invisible to standard astronomical imaging. Infrared surveys like WISE and Spitzer can detect young, warm rogues within a few hundred light-years, but older, colder rogues emit virtually no detectable radiation. They're simply too cold and too small. Gravitational microlensing works, but only when precise alignments occur, a geometric probability of roughly 1 in a million for any given rogue. We've detected dozens through this method, but trillions remain undetected. The next generation of telescopes might change this. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct microlensing surveys orders of magnitude more sensitive than current efforts. Estimates suggest Roman could detect thousands of rogue planets, including Earth mass rogues, and provide detailed statistical data on the population distribution. The European Space Agency's Euclid mission, launched in 2023, adds another dimension. While primarily designed to study dark energy, Euclid's wide-field surveys might catch rare microlensing events involving nearby rogues, potentially providing the first optical images of these objects as they briefly magnify background galaxies. But even with these advanced instruments, we'll detect only a tiny fraction of the total population. Most rogues will remain forever invisible, known only through their statistical signatures in microlensing data.
This forces us to reconsider fundamental assumptions about planets and their role in the cosmos. For centuries, we defined planets by their relationship to stars. The word planet comes from Greek planetes, meaning wanderer, but this referred to wandering among the fixed stars, not wandering through the void alone. The International Astronomical Union's 2006 definition of planet explicitly requires orbit around the Sun or another star. By this definition, rogues aren't planets at all. They're free-floating planetary mass objects. But functionally, they're worlds. Many retain moons, atmospheres, possibly oceans, and even life. They formed through planetary processes. They possess planetary properties. The only difference is their current trajectory. This raises profound questions about cosmic structure and meaning. Is a planet defined by its origin, its properties, or its context? Is Earth a planet because it orbits the Sun, or because it's a rocky world with certain characteristics? If Earth were suddenly ejected, flung into interstellar space by a gravitational encounter with a rogue Jupiter, would it cease to be a planet? It would retain its mass, composition, geology, and even its moon. Only its relationship to the Sun would change. Yet, by our definitions, it would no longer be a planet. Dr. Jean-Luc Margot at UCLA has proposed alternative definitions that focus on intrinsic properties rather than orbital status. By such definitions, rogues would be planets, orphaned perhaps, but planets nonetheless. The debate matters because it reflects how we conceptualize cosmic architecture. Are solar systems the fundamental units of galactic structure, with rogues as mere debris? Or should we view the galaxy as a vast planetary system, with most planets unbound to individual stars? The answer changes how we understand our place in the cosmos and what we mean when we count the planets in our galaxy. Finding rogues requires creative approaches. The Nancy Grace Roman Space Telescope's microlensing surveys will revolutionize detection. Roman will monitor hundreds of millions of stars simultaneously, watching for the brief brightening events that signal rogue transits. The mission's sensitivity should enable detection of Mars-mass rogues and potentially even Moon-mass objects if they pass in front of particularly bright background stars. Roman will provide not just detection, but characterization. The exact shape of a microlensing event's light curve reveals the mass of the lensing object. Duration indicates whether it possesses bound companions, moons, or planetary companions. Multi-wavelength observation during events might even provide spectroscopic data on atmospheres if the rogue is warm enough. But other strategies exist and put limits on how many rogues exist in our galaxy, especially those large enough to harbor significant submoons or atmospheres.
Dr. Jackie Faraday at the American Museum of Natural History leads efforts to identify nearby rogues through their infrared signatures and proper motion. Even cold rogues might be detectable at close range, within 10 to 20 light-years, if they're still warm enough to emit faint infrared radiation. By measuring their apparent motion across the sky over years, astronomers can identify objects moving independently of stellar background patterns. Several candidates have been identified through this method. Most turned out to be brown dwarfs rather than planetary mass objects. But the technique continues to improve, and future infrared surveys, like those planned for the extremely large telescope, might detect cold rogues within 30 light-years of the Sun. A more speculative approach involves looking for atmospheric auroras. Even a cold, dark rogue might produce faint auroral emissions if it possesses a magnetic field and travels through regions of ionized interstellar gas. These emissions would be extraordinarily faint, but potentially detectable with extremely sensitive radio telescopes. If we identify a nearby rogue, could we visit it? In 2018, the Initiative for Interstellar Studies published a mission concept for a rogue planet flyby. The study examined the feasibility of intercepting a rogue passing within 100 astronomical units of the Sun, closer than the inner Oort cloud. The challenges are immense. A typical rogue travels at 30 to 50 kilometers per second relative to the Sun. Earth orbits at 30 kilometers per second. A spacecraft would need to match the rogue's velocity vector, a delta-v budget potentially exceeding 50 kilometers per second for an intercept mission. Current chemical rockets can achieve perhaps 10 kilometers per second. Even nuclear thermal propulsion tops out around 20 kilometers per second. Reaching the necessary velocities would require either multiple gravitational assists using the outer planets, adding years or decades to the mission, or advanced propulsion systems like nuclear electric or fusion drives, or an extremely fortuitous rogue that happens to be traveling on a trajectory nearly parallel to Earth's orbit. Despite these challenges, a close encounter remains scientifically tantalizing. Instruments on a flyby mission could measure the rogue's mass, size, temperature, atmospheric composition, magnetic field, and presence of moons. If the rogue is young and warm, infrared spectrometry could detect atmospheric chemistry and surface properties. More ambitiously, some researchers envision an impactor mission, deliberately crashing a probe into a rogue's ice crust to excavate subsurface material and analyze it spectroscopically from a trailing spacecraft. This technique, similar to NASA's Deep Impact Comet mission, could reveal whether liquid water exists beneath the ice and whether it contains organic compounds or biomarkers. The most speculative proposals involve soft landing on a rogue. A small probe could study surface geology, drill through surface ice, and potentially access subsurface oceans. The mission would require decades of flight time and technologies that don't yet exist. But for understanding these orphaned worlds, it might represent humanity's best opportunity. Some researchers have proposed an even more radical idea, using rogues as interstellar transportation. Dr. Irina Romanovskaya at Houston Community College published a paper in 2019 exploring this concept. If a civilization could establish a self-sustaining colony on a rogue planet, building habitats beneath the surface ice, using geothermal energy, and developing closed-loop life support, that civilization would essentially own a mobile world. The rogue travels through interstellar space. Over millions of years, it passes near various stellar systems. A sufficiently advanced civilization could use the rogue as a generation ship, riding it between stars, periodically using advanced propulsion to nudge its trajectory toward desirable destinations. The advantages are significant. Immense mass provides radiation shielding and raw materials, geothermal energy available for millions or billions of years, subsurface oceans potentially usable for life support, no need for artificial gravity, the planet provides it, room for enormous populations. The concept isn't as absurd as it might initially seem. We already have the theoretical knowledge to build subsurface habitats. The technical challenges involve energy production, life support recycling, and psychological factors of permanent isolation. But these are engineering problems, not physics problems. More intriguingly, if such colonization is possible, it might already be happening. Technological civilizations elsewhere in the galaxy, facing extinction from stellar events or resource depletion, might choose to migrate to rogues rather than attempt the enormous energy expenditure of conventional interstellar travel. From Earth, we would see nothing. No radio signals, no optical signatures, just a frozen world drifting through the darkness, potentially harboring billions of inhabitants living in complete isolation beneath kilometers of ice, powered by their planet's slowly cooling core. Could we detect such inhabited rogues? Dr. Manasvi Lingam at the Florida Institute of Technology has proposed several theoretical signatures. Thermal anomalies. A inhabited rogue might show infrared hotspots where subsurface habitats release waste heat through the ice crust. These would appear as localized temperature elevations, perhaps a few degrees warmer than the surrounding surface. Atmospheric contamination. Industrial activity might release gases that seep through the ice and create detectable atmospheric signatures. Even small quantities of industrial byproducts could be spectroscopically detectable if we observe the rogue during a microlensing event. Magnetic field irregularities. Large-scale industrial activity or technological infrastructure might generate local magnetic field variations, detectable through radio observations. Artificial lighting. While seemingly absurd for a world without a sun, civilizations might use external lighting for surface operations or simply for psychological benefit. Extremely sensitive optical telescopes might detect faint illumination if a rogue passes close to the solar system. The probability of detecting any of these signatures is vanishingly small, but not zero. The James Webb Telescope and future instruments possess the spectroscopic sensitivity to detect industrial pollutants in exoplanet atmospheres. If applied to warm rogues during a microlensing event, the same techniques might reveal biosignatures or technosignatures. The concept extends to SETI. The traditional search for extraterrestrial intelligence focuses on radio signals from planetary systems. But perhaps we should also search for signals from rogues. Not constant transmissions, which would serve no purpose, but occasional beacons designed to attract attention from passing civilizations or starships. A civilization living on a rogue might periodically broadcast their location simply to maintain contact with the galactic community, despite their isolation.
Recent breakthroughs suggest rogues might play a role in galactic-scale chemical evolution. When a planet is ejected, it carries with it whatever chemical composition it possesses. heavy elements forged in the death of previous generation stars. These elements, locked in the rogue's composition, travel through interstellar space, potentially getting incorporated into new star-forming regions. Dr. Fred Adams at the University of Michigan has modeled this chemical transport mechanism. His simulations suggest that rogues act as chemical couriers, carrying heavy elements from one region of the galaxy to another over millions of years. When a rogue eventually enters a star-forming nebula, it can be accreted by the growing protostellar disk, enriching the chemical composition of new stellar systems. This process might be responsible for some of the chemical diversity we observe in stellar populations. Stars with unusual chemical abundances might have formed from material enriched by the accretion of rogues carrying atypical element ratios. More speculatively, rogues might facilitate panspermia, the transfer of life between stellar systems. A rogue harboring subsurface life that passes through a star-forming region might seed that region with organic compounds or even viable microorganisms. When new planets form and stabilize, they might inherit biological material from the rogue, jump-starting local biochemical evolution. The timescales are vast, millions of years for a typical rogue journey between stellar encounters. But life, once established, can persist for geological timescales. Frozen but viable microorganisms could survive millions of years in a rogue's subsurface ocean, only to be released when the rogue encounters a new stellar environment. If this mechanism operates across the galaxy, life might not emerge independently on each inhabited world. Instead, rogues might create a galactic biosphere, a connected web of life distributed across stellar systems by wandering worlds acting as biological transport mechanisms. The most profound implications emerge when we consider not just individual rogues, but the population as a whole, moving through the galaxy's spiral arms, passing through star-forming regions, occasionally interacting with established solar systems. They represent a dynamic, evolving component of galactic structure, not dead worlds floating aimlessly, but active participants in the galaxy's ongoing evolution.
The ultimate question about rogues: can they sustain life? Traditional definitions of habitability focus on the habitable zone, the region around a star where liquid water can exist on a planet's surface. By this definition, rogues are absolutely uninhabitable. No star means no habitable zone. But the assumption that life requires starlight is Earth-centric and possibly wrong. Earth itself hosts ecosystems completely independent of sunlight. Deep-sea hydrothermal vents support complex food webs powered by chemosynthesis. Underground caves harbor microbial communities that derive energy from rock-water interactions. Antarctic subglacial lakes, isolated from surface conditions for millions of years, contain viable bacteria. None of these environments require sunlight. They require only liquid water, chemical energy, and the right conditions for biochemical reactions. A rogue planet with geothermal activity and subsurface oceans provides all three. Dr. Dorian Abbott's simulations suggest that a planet with Earth's internal heat budget, if ejected, could maintain liquid subsurface oceans for billions of years through radioactive decay and residual core heat alone. Add tidal heating from a large moon, and those oceans could remain liquid, potentially indefinitely. The ultimate habitability paradox emerges.
Rogues might actually be more stable environments for life than sun-orbiting planets. Consider Earth's history. Life has been periodically threatened or disrupted by solar flares and coronal mass ejections, asteroid impacts, ice ages triggered by orbital variations, and atmospheric loss from stellar wind exposure. A subsurface ocean on a rogue experiences none of these threats. The environment remains constant, thermally stable, chemically stable, protected by kilometers of ice from radiation and impacts. Once life establishes itself, it could persist unchanged for billions of years. The deep oceans of Earth have remained relatively stable in temperature and chemistry for hundreds of millions of years. A rogue's subsurface ocean would be even more stable. No tides, no seasonal variations, no sunlight-driven surface processes to perturb the environment. This stability might make rogues superior to conventional planets as habitats for complex life. If rogues can sustain life, the implications multiply rapidly. With trillions of rogues in the galaxy, even a small percentage harboring life would create an enormous dark biosphere, life existing in environments completely invisible to conventional astronomy. Dr. Dimitra Atri and Dr. Abraham Loeb have proposed that the galactic biomass might actually be dominated by life on rogues rather than life on illuminated planets. Their reasoning: if 0.1% of rogues harbor life, 1 in every 1,000, that's still billions of inhabited worlds in the Milky Way alone. Each might host subsurface oceans containing biomass comparable to Earth's deep ocean ecosystems. The total biomass could exceed that of all conventional habitable planets combined. Moreover, life on rogues would experience entirely different evolutionary pressures. Without sunlight, photosynthesis never evolves. Energy comes entirely from geochemical sources. Ecosystems would resemble Earth's hydrothermal vent communities, but evolved across billions of years in complete isolation. What might such ecosystems look like after 4 billion years of evolution in eternal darkness? On Earth, vent ecosystems are relatively simple, mostly bacteria and specialized animals like tube worms and crustaceans. But these ecosystems are young, isolated, and constantly disrupted by tectonic activity that eventually closes the vents. On a rogue, subsurface ecosystems could achieve enormous complexity over geological timescales. Given stable conditions and billions of years, what's the upper limit on biological complexity in darkness? Some researchers speculate about intelligent life arising in such environments. While seeming unlikely, intelligence on Earth correlates with vision, which requires light. Intelligence fundamentally requires only information processing and environmental complexity. A sufficiently complex dark ecosystem might evolve organisms with alternative sensory systems, chemical sensing, electrical field detection, echolocation, or entirely alien modalities we haven't conceived. An intelligent species evolved on a rogue would have no concept of stars, light, or the visible universe. Their understanding of reality would be profoundly different from ours, shaped by eternal darkness, stable environments, and chemical rather than optical information. The dark biosphere hypothesis offers a potential solution to the Fermi paradox. Enrico Fermi famously asked, if intelligent life is common in the galaxy, where is everybody? We see no evidence of alien civilizations, despite the statistical expectation that they should exist. Many solutions have been proposed. Perhaps intelligence is rare.
Perhaps civilizations destroy themselves. Perhaps interstellar travel is impossible. Perhaps we're looking in the wrong places or at the wrong times. Or perhaps civilizations predominantly arise and remain on rogues. A civilization on a rogue faces unique challenges. No raw materials from asteroid mining. Everything must come from the planet itself. No solar energy. All energy comes from geothermal sources. No reason to build radio transmitters or optical beacons because there's nothing nearby to communicate with. Such civilizations would be entirely invisible to SETI searches. They wouldn't build megastructures like Dyson spheres because there's no star to enclose. They wouldn't emit technosignatures we'd recognize because their technology would adapt to their unique environment. More fundamentally, a civilization on a rogue has less motivation for space exploration. Earth civilizations look to the stars partly because we see them. They're visible, beautiful, inspiring. A rogue civilization sees only darkness. The concept of other worlds might never occur to them, or if it does, might seem impossibly distant and unreachable. They would develop deep expertise in geology, biochemistry, material science, and energy engineering, everything needed to sustain themselves in their isolated environment. But astronomy, astrophysics, and cosmology might never develop beyond theoretical speculation. The Fermi paradox might resolve simply. Most civilizations exist, but they're living in permanent darkness, isolated on wandering worlds, entirely invisible to us, and likely unaware that illuminated planets like Earth even exist.
Some researchers have proposed creating a comprehensive catalog of nearby rogues to prepare for future exploration. The Nancy Grace Roman Space Telescope will dramatically expand our detection capabilities, potentially identifying thousands of rogues through microlensing surveys. But microlensing only provides mass and approximate distance, not precise location or trajectory. Follow-up observations with other instruments could narrow the uncertainties. By combining microlensing data with proper motion measurements from the Gaia spacecraft and infrared surveys from JWST, astronomers might triangulate precise positions and velocities for rogues within several hundred light-years. Dr. Corin Baylor-Jones has proposed the Local Rogue Census, a coordinated observational campaign to identify and characterize every rogue within 100 light-years. The catalog would include estimated mass from microlensing data, 3D velocity vector from astrometric measurements, temperature and atmospheric composition from infrared spectroscopy, presence of moons or companions from microlensing light curves, and future trajectory predictions. Such a catalog would serve multiple purposes. It would identify rogues on trajectories bringing them closer to the solar system, enabling future flyby missions. It would provide statistical data on the local rogue population density and mass distribution, and it would identify the best candidates for detailed study, particularly warm rogues with atmospheric signatures or rogues with large moons. One tantalizing possibility, identifying rogues on intercept trajectories. A rogue passing within 50 astronomical units of the Sun, roughly the distance of the Kuiper Belt, might be accessible to future propulsion technology. If identified decades in advance, a mission could be designed and launched to arrive during the closest approach, maximizing scientific return while minimizing delta-V requirements. The catalog might even include rogues that have already passed through our neighborhood and are now receding. While no longer accessible for missions, these objects could be studied through long-term astrometric and photometric monitoring to understand their properties and validate theoretical models.
A darker question: could a rogue threaten Earth? The probability of direct impact is vanishingly small. The solar system is vast, mostly empty space. A rogue would need to pass not just through the general vicinity, but through the incredibly small volume occupied by Earth's orbit at precisely the right moment. The odds against this are astronomical, perhaps 1 in trillions per year. But rogues don't need to impact to cause disruption. A massive rogue, Jupiter mass or larger, passing through the outer solar system could gravitationally perturb planetary orbits. The effects would be subtle initially, small changes in orbital eccentricity or inclination, but could accumulate over millennia as significant climate impacts as Earth's distance from the Sun varies. More immediately threatening, Oort cloud perturbation. A rogue passing through the inner Oort cloud would gravitationally scatter countless comets. Some would be ejected into interstellar space, others would be sent falling toward the Sun. Over subsequent centuries, Earth might experience elevated impact rates as these perturbed comets reach the inner solar system. Could this be detected in advance? Potentially. If the local rogue census identifies a massive object on a trajectory that will bring it within 1,000 astronomical units of the Sun, astronomers could predict the encounter years or decades in advance. Modern sky survey systems like Pan-STARRS and the upcoming Vera-Rubin Observatory would detect incoming comets months or years before potential impacts, providing warning and potentially enabling deflection missions. The more subtle threat involves long-term accumulation of close encounters. Over millions of years, repeated rogue passages near the solar system might gradually destabilize the orbits of outer planets, creating chaos that eventually propagates inward to the terrestrial planets. Some models suggest that the solar system's long-term stability, our ability to survive for billions of years, might depend partly on how frequently rogues pass nearby. We've been lucky so far. No catastrophic encounters in Earth's 4.6 billion-year history. But statistically, such encounters must occur. Somewhere in the galaxy right now, a rogue is colliding with an inhabited planet, or gravitationally disrupting a stable solar system, or sending a storm of comets toward an unsuspecting civilization. The galaxy is vast, but far from empty, and the wanderers are always passing through. We began with a simple question: what are rogue planets? The answer transformed into something far more profound than we anticipated. Rogue planets aren't anomalies or rare exceptions. They're fundamental components of galactic structure, possibly outnumbering stars themselves. They represent the accumulated debris of 12 billion years of planetary system formation and evolution. Every rogue tells a story of creation, survival, and eventual exile. Some formed around stars and were thrown into darkness. Others condensed directly from interstellar gas, never knowing the warmth of a sun. All now wander through the void between stars, invisible, silent, yet profoundly present.
They constitute a significant fraction of the galaxy's baryonic mass. They transport chemical elements across vast distances. They might harbor life, perhaps vast quantities of life in dark subsurface oceans, evolved across billions of years in environments we can barely imagine. The galaxy we thought we understood, a collection of solar systems floating in mostly empty space, is actually something far richer and stranger. It's filled with worlds, trillions of them, most forever dark, forever isolated, yet fundamentally planetary in nature. Our definitions of planet and solar system proved inadequate. A planet doesn't require a sun. A solar system isn't the fundamental unit of galactic structure. These concepts are Earth-centric, shaped by our local experience rather than cosmic reality. The true galactic architecture is more continuous than discrete, a vast population of objects at all scales, from dust to supermassive black holes, with rogues representing a massive middle tier we only recently recognized.
Where does the science stand today? The existence of rogue planets is now established beyond doubt. Multiple independent detection methods, gravitational microlensing, direct infrared imaging, proper motion surveys, all converge on the same conclusion. The galaxy contains a vast population of free-floating planetary mass objects. The exact numbers remain uncertain. Estimates range from hundreds of billions to several trillion, depending on assumptions about the mass distribution and formation mechanisms. But all estimates agree, rogues vastly outnumber stars. Current research focuses on characterization rather than mere detection. The James Webb Space Telescope conducts infrared spectroscopy of young rogues, analyzing their atmospheric composition and thermal structure. The Nancy Grace Roman Space Telescope, launching soon, will provide unprecedented statistical data on the rogue population's demographics. Ground-based efforts continue. The Vera Rubin Observatory's Legacy Survey of Space and Time will monitor billions of stars, potentially catching rare microlensing events involving nearby rogues. The Extremely Large Telescope will search for cold rogues through direct infrared imaging. Theoretical work explores habitability questions. Can rogues sustain life? Under what conditions? What might such life look like? These questions transition from speculation to serious astrobiology, with implications for SETI and the search for habitable environments throughout the galaxy. Mission concepts under study include rogue flyby missions, rogue landing missions, and even proposals for establishing research outposts on nearby rogues, if any are found within accessible range. The scientific consensus: rogues are real, numerous, and fundamentally important to understanding galactic structure and evolution. What remains uncertain is their exact population, their individual properties, and whether they harbor life.
Consider what this means for humanity's place in the cosmos. We thought we lived in a solar system within an otherwise empty galaxy. We've learned we actually live in a galaxy filled with worlds, most of them wandering alone through darkness. Every night, when you look up at the stars, remember, between those points of light drift countless worlds, frozen planets tumbling through the void, ice-covered oceans kilometers deep. Possibly life, evolved in darkness across billions of years. Possibly civilizations, living beneath frozen crusts, powered by their planet's dying warmth, unaware that illuminated worlds like ours even exist. Some of those worlds pass within light years of Earth. Some might pass even closer. We can't see them. We can only infer their existence through subtle gravitational effects when they happen to align perfectly with distant background stars. The universe is stranger, fuller, more complex than we imagined. What we see represents a tiny fraction of what exists. Most of reality is dark matter, dark energy, and now we realize dark worlds, planets without suns, wandering the galaxy in permanent night. This realization should humble us. Our experience, life on an illuminated world, warmed by a nearby star, seeing the universe through the electromagnetic spectrum, is the exception, not the rule. Most planets experience reality differently. Most worlds are dark, cold, isolated. Yet those worlds are still worlds. They have geology, possibly atmospheres, potentially oceans and life. They're not lesser because they lack a sun. They're simply different, following an alternate path through the possibilities of planetary existence. Perhaps we should envy them. A rogue planet experiences no solar flares, no asteroid bombardments, no ice ages triggered by orbital variations. Life on a rogue, if it exists, would inherit an environment of remarkable stability. Darkness, yes, but also constancy, safety, peace.
We've journeyed through evidence, theory, and speculation, yet fundamental mysteries remain. We don't know if rogues harbor life. We have theoretical arguments suggesting it's possible, even likely, but we have no direct evidence. The question awaits future missions, future telescopes, future discoveries. We don't know the exact population. Is it 500 billion? 2 trillion? The uncertainty spans factors of 4 or more. We need better statistics, more detections, refined models. We don't know if intelligent life has arisen on rogues. The idea seems unlikely, yet cannot be dismissed. If such civilizations exist, they would be completely invisible to us, and we to them. Two forms of intelligence, existing in the same galaxy, forever unaware of each other. We don't know if rogues have ever posed threats to Earth. Statistical models say close encounters must have occurred, but we have no confirmed evidence of specific events. The question remains open. We don't know what we'll find when we finally visit one. Will we discover frozen wastelands, sterile and lifeless? Or will we find subsurface oceans teeming with alien biochemistry, evolved across eons in eternal darkness? Most profoundly, we don't know what rogues tell us about the universe's ultimate nature. Are they simply byproducts of planetary formation, debris from violent gravitational interactions? Or do they represent something more fundamental about cosmic structure, a natural equilibrium state that most planets eventually reach?
In a universe that tends toward entropy, toward heat death, toward the gradual dissipation of all structure, perhaps rogues represent a preview of the far future. Billions of years from now, when stars have exhausted their fuel and galaxies have dispersed, perhaps most remaining worlds will be rogues, frozen, dark, alone, wandering through a darkening cosmos, carrying the chemical heritage of long-dead stars, perhaps harboring the last remnants of life, existing in the final habitable environments the universe provides before the ultimate cold. The wanderers will still be there, tracing their paths through the void long after the last star fades.
The universe is vast. The mysteries are endless. The journey continues. And somewhere in the darkness between stars, a world passes through the night, unseen, unknown, yet profoundly real. Perhaps it harbors life. Perhaps it once knew the warmth of a sun. Perhaps it contains the ruins of civilizations or the seeds of life yet to bloom. We cannot see it, but we know it's there. And now, so do you.